Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We will do our best to answer the questions at the end and to follow up with any unanswered questions via email. As I think you may know, these Tech Talks have been designed to provide straightforward insights into radio frequency components. We'll talk about the related technologies and some of the extra design and engineering value that is added by a custom manufacturer, such as Quantic TRM. To begin today's session, I'm once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore, the author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies. Shaun has been with Quantic TRM since the late 90s. And his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yeah, thank you, Paul. So what we're going to talk about today here really is about multi-octave beamforming. So I think the way to start here is the first thing we'll do is define what multi-octave really means. And what impact does that have when we're talking about beamforming? We'll then go through some advantages of a multi-octave beamformer, as well as the disadvantages. It's not always a win-win. And then we'll talk about some of the performance differences and what do you have to give up and what do you gain by going with a multi-octave beamformer. We'll talk about some Quantic TRM differentiators, and then we'll wrap it up with a summary.
Terrific. And maybe to get started, can you define multi-octave beamforming?
Sure. Well, the term multi-octave really, first you have to really understand what an octave is. And an octave is defined in the RF world as something having a 2-to-1 bandwidth, or the high frequency is twice that of the low frequency. That defines an octave. An octave goes back to the old waveguide bands. Most of those were octave bandwidths, and it became very evident in our industry that because of those limitations, that was the kind of technology that we typically work with, and almost virtually all components tend to work over an octave bandwidth. That sort of bandwidth is referred to as kind of a standard band. Narrow band is less than an octave, and wide band is more than an octave. So really what we're looking to talk about here are beamformers that have a greater than 2-to-1 bandwidth, high frequency divided by low frequency. Now, typical applications and configurations of multi-octave beamformers are usually things where things like Butler matrices or monopulse comparators, where you're going in there and trying to utilize the fact that you have these broad ranges of things that you want to either track or just identify where information is coming from. Other sorts of configurations are some difference mode formers, some phased array signal distribution networks as antennas are becoming broader and broader bandwidths. And also we do some very broad stuff for any kind of very specialized antenna feed network, such as adding a Taylor weight to an antenna feed. All these things can have multi-octave applications, and what we're going to talk about today really are, what are the trade-offs when we go in there and we do have these multi-octave sort of trade-offs.
Okay, so what are the advantages of this type of beamforming?
Sure. One of the biggest advantages of going into a broadband sort of application is you can collect more data when you're coming in at a broadband, assuming that your antenna aperture has the bandwidth. You also can use the same beamforming network for a variety of antenna feed networks, or if you have 2 locations that have a similar sort of configuration, except operating different bands, you can very often use the same beamformer for both applications, and therefore help minimize part number count and those sorts of things. Also help with redundancies and other sorts of things that you think about in the field as far as how many beamformers are you going to stock in the field. So it has those sorts of good sources of applications. Also, if you're talking about a broadband antenna, you can eliminate the need for a multiplexer before you hit into your beamforming network by having it all done in one step. Or like I mentioned earlier, you can use the same part number in various system configurations.
Okay, so if those are the pluses, how about some of the disadvantages?
Okay, so the different disadvantages really start running into basically because of how we have to build a broadband beamformer. There are certain, sort of negative baggage that comes along with it. The first is that most of these sorts of devices require that we go in there with a multi-stage transformer or distributed network. As soon as we start going into a multi-stage or cascaded sort of networks, you have higher line losses because of copper. It is just, the circuit is going through a longer path, therefore it's going to have increased insertion loss. As we move into some of these longer packages, we start running into some packaging constraints and configuration issues. As lines get bigger, it gets harder and harder to package these things together. So that actually comes in there and starts to become an issue. Increased connector spacing is something there that as you're looking at, for example, a 90-degree hybrid and you have to put 3, 4, 5 sections in there, what happens there is that the connector spacing between the two ends of that transformer get farther and farther apart. Part of how we help mitigate some of that typically is we go to a multi-layer structure, which adds yet another layer of complexity to the manufacturing and design of this. And as we get more and more complicated with these designs, there's more opportunity for things to detune, as well as making it harder to tune, because a lot of the narrowband techniques that a lot of people use in the industry become much less effective when you're trying to build a broadband structure. The structure really has to work really well, and there really is no narrowband kind of technique that can improve performance without negatively impacting the performance someplace else. So it really becomes a much more difficult part to build. So you're adding more complexity, larger sizes, higher insertion losses, as well as some of the detail performance. Because of the increase in bandwidth, you will pay a penalty in other performance aspects, but things like phase matching, as well as amplitude matching, and VSWR will typically degrade as well. Sort of on top of all that, because we have to add more line length, it really becomes kind of obvious that the parts need to get larger, and with larger sizes come larger weights. So whereas it can be good to go in there in certain applications, to go in there and go with a multi-octave beamformer, and sometimes you have to, because of the bandwidth of the data that you're looking at, or because the aperture requires that much bandwidth. Always realize that bigger is not always better, and more bandwidth is not always better for the overall system performance. So we just got to go through. We have to kind of bounce those off each other, make sure that really what we're looking at is makes sense for the overall system. And this is a good example here of one of the trade-offs as far as what happens when you start looking at phase and amplitude balance. The graphic that's on the left is a broadband device, and what you see there is this very periodic sinusoidal sort of mismatch error that happens as you start cascading long transformers. The narrative on the right of the screen over there is a narrowband device, and again, the errors here are for the most part very linear. And in this case over here, they can be readjusted in a much more uniform way to bring them in there and have a better match. Whereas the device that's on the left with that sort of sinusoidal ripple, it becomes you really can't make any one of those better, because as you degrade one, the one next to it just you can't make one better without making the other one worse, and so your overall RMS of the system is actually quite good. However, on an individual patch, you can have high errors.
Well, excellent, and great information as usual. Would you like to summarize?
Sure. So basically, what we like to look at here as far as to when we start talking about any kind of broadband network, whether it be a beamformer or any other device, is you always have to understand the trade-offs that are incurred by trying to increase bandwidth. Bandwidth is never a free commodity. It always comes at a price. Sometimes it comes at insertion loss. Sometimes it comes at our ability to either amplitude or phase match. There are lots of reasons as to why you'd like to do it or need to do it. There are other times when where it may not be quite so advantageous. So a good example of that is if you have multiple locations of where you're going to put this, and the beamformer itself will only ever operate over a narrow band. Then really what you want to have is you want to make sure that you have a like to have, which is use one component for multiple spots in the system. It's very different than having a must have, which is the beamformer has to work over this band to this band and have some very good insertion loss and very good phase tracking characteristics. And it's always important to go through there and go through all those trade-offs and make sure that really what you're asking for is really what the system needs. And very often that comes down to what is a must-have for the system versus what is a like to have or a nice to have for the system or for future performance. Broadband beamformers can certainly always be built, but just realize that there's always some trade-off that needs to get made.
So finally here, what are some of the unique aspects or differentiators that Quantic TRM brings to the table with respect to beamforming?
Sure, and I want to say here, this is something that really goes across the board, not just with beamformers. Quantic TRM loves to work with our customers and going in there and solving unique problems. So really, we like to go through there and make sure that the component and device and the design that we're going to be delivering to our customers is the absolute best solution for their needs. And as part of doing that, we're going to go through there, find out exactly what the application is going to be, find out what's important to the customer, what are the need to haves for any particular design. Once we have that information, we're going to go back. We're going to carefully work on configuration of a design. We're going to select materials, the way we design the packaging. All those things will come into making sure that what the part that the customer gets will meet the full needs. And it's not just the electrical design, it's the mechanical design, it's the packaging, it's the handling, it's all the data that goes along with it. And like I said, part of what we love to do is make sure that the customer gets the best value for their dollar, which includes hardware as well as data, and the testing that goes along with it, and all the objective evidence that's required to make sure that the part that they get really is the part that they need and is the best fit for the solution.
Well, thank you, Shaun. We do have one question, which is for broadband components, why do the sinusoidal errors that you mentioned emerge?
Yeah, that's a great question, Paul. So really the reason for that is if you look at any distributed network, especially for a 90-degree or 180-degree hybrid, what you have is that the coupling the coupling transformer is not a flat digital sort of thing. There is a curve that goes across those transformers as that individual element changes its phase relationship with the arm that it's coupling to. So by its nature, passive networks are never exactly linear. There's always a little bit of a curve to them. And what happens is that once you start cascading them, we apply a Chebyshev transform to those, which gives us an equal ripple function across the bandwidth. Now, an equal ripple function by itself has a sinusoidal sort of variation, equal amplitude across the operating bandwidth. As you cascade these elements, what happens is if they all are operating over the exact same bandwidth, those errors will align, and in some cases they'll subtract, but yet in other cases they will add. And therefore, what you'll get is this very well-defined sinusoidal sort of error that happens whenever you start cascading these sorts of distributed elements. Like the graphic that I showed earlier in this presentation, what you get is some of those graphs will actually add, and we'll see, well, gee, that the error is getting worse and worse and worse at this point, and you will see some of the paths where the error is quite a bit less, and that's because at one point those errors actually subtracted or added in the correct direction, making the overall error less. What makes it difficult here is that the error, when you start getting to these very complicated sort of beamformers, some of those worst case errors can become significant, and it's just something you just have to be very careful of as you're going through your design and making those decisions.
Okay, well, thank you once again, Shaun, and thanks again to all of you for joining us. In summary, I think that the bullets on the screen speak for themselves. Going forward, if you are a customer and have more questions, or if you'd like to discuss details with one of our engineers, we'd love to hear from you. Please feel free to call the engineering hotline. The number is on your screen, 888-677-6877. There are no costs, of course, for these calls. If you're one of our field sales representatives, then you know your calls are also welcome all the time, and you can certainly submit questions directly through the sales rep portal on our website. In case it's helpful, our next Tech Talk will be on Tuesday, March 21st at 1 p.m. Eastern, and the topic will be SWAT-C solutions. Thank you, everyone.
Thank you, Paul.